We're looking at Chapter 7, Section 7.4. In this lesson, we're going to look at solving exponential equations using logarithms. So let's recall changing from logarithmic form to exponential form. We have the log form. We have log of an argument to the base b is equal to e. If we change it into exponential form, we have the base and the exponent would equal the argument. For example, log 27 base 3 equals x. When changing it to exponential form, that will give us 3 to the power of x equals 27. When looking at the natural log function, here the base would be e, and the exponent would be y, and of course the argument would be x. We also have to remember that evaluating logs. Here we have the change of base formula. And so, if for example we had something like the log of 27 base 5, that would be equal to log 27 divided by log 5. And we can calculate log 27 divided by log 5 on our calculator since it's base 10. Let's also recall the laws of logarithms. We have the sum of two logs with the same base. We can multiply m and m when we combine to a single log. When we have the difference of two logs with the same base, we can combine m and n, or combine the logs, to a single logarithm by doing the quotient of m and n. And when we have m to the power of n, we can bring it down in front and multiply it by log m base a. So we have to recall the laws of logarithms as well. Let's look at an example. We did examples like this. Since 1 over 81 could be written as a base of 3, we could have 3 to the power of x subtract 1 would equal 3 to the negative 3, since that's what 1 over 81 is, to the 2x subtract 1. So that will give us 3 to the x subtract 1 equal to 3, using the distributive property here, negative 6x plus 3. Then we can, now since we have two powers that are equal to each other, and they have the same bases, we can let the exponents be equal to each other. And so we would have x plus 6x is equal to 3 plus 1, so 7x would equal 4. Therefore, x would be 4 over 7. So that is up until now. Now we're looking at something like 4 to the power of x subtract 1, which will equal 21. Here, 4 to the power of 2 is 16, and 4 to the power of 3 is 64. We cannot write 4 and 21 as a power with the same base. So here, we can take the log of both sides, and this will work for any exponential equation. You could take the log of both sides of the equation to preserve equality, of course. And this log is log base 10. This log that we're using, the log that we can calculate this log on our calculator. Now, using the power rule, we're going to bring x plus 1 in front and multiply it by log 4. So that would be x subtract 1 multiplied by log 4. Here now, we can use the distributive property. We can have x times log 4 subtract 1 times log 4. We would have x times log 4 subtract 1 times log 4. And that will give us log 21. Now we're going to leave the term with the variable here, and we're going to move this one to the other side of the equation. That will give us x log 4, which will be equal to log 21. We could calculate these numbers on the calculator. Log 21 plus log 4. We can calculate these numbers on a calculator now, since they are base 10. Now we can have x log 4 will be equal to, we can use the laws of logs and combine. If we do not do this step, we can still be correct. And we would have log 84, since 21 times 4 is 84. And to solve for x, that would give us log 84 over log 4, which now we can calculate. That will give us 3.19, so approximately. Sorry, it's approximately 3.19. So any of these steps, we could use the calculator to get our decimal number. Right here, we could use, we could calculate log 4. We could calculate this log 4. We could calculate 21. Here, it's not necessary to combine these logs and make a single log, although it is the laws of logarithms, so that is why I used this in my solution. And then divide by log 4. And once again, you get here, you can use your calculator to go log 84 divided by log 4 to give us 3.19. Let's have a look at another example. Since I cannot write 5 and 104 as a power with the same bases, I will take the log of both sides of the equation. Once again, I can do this because we're preserving equality. Now I will use the power law of logs to take the x plus 2 and bring it in front of the log to multiply it by log 5. So that would be x plus 2 log 5, which will equal log 104, which I can calculate. I can calculate this log 104 and get a decimal number on the calculator right now. I will now use the distributive property and multiply each x and 2 by log 5. So I'd have log 5 times x and log 5 times 2. So this would be x log 5 plus 2 log 5, which will equal log 104. I will now have, I'm going to move this on the other side. I would have x log 5 is equal to log 104 subtract 2 times log 5. Now since x is being multiplied by log 5, I can divide both sides of the equation by log 5 to solve for x. X will equal log 104 subtract 2 times log 5 divided by log 5. This will give us approximately 0.8857 for x. Now I could do it in such a way, I could simplify this a little more. I could say that this is log 104 subtract log 5 squared over log 5. And then in continuing with the laws, I could say that that's log of 104 over 25 divided by log 5. Using the laws of logs, I will combine the difference here by doing the quotient. And then if I take the log of 104 over 25 and divide it by log 5, I would still get the 0.8857. Let's do another example. Notice that there are powers now on both sides of the equation. I will still take the log of both sides. And I'll use the power rule to bring the x subtract 1 to multiply by log 2, and the x plus 1 then to multiply by log 3. Now I'll use the distributive property and multiply both the x subtract 1 by log 2. So that'll be x times log 2 subtract 1 times log 2. And I'll do the same on the right side of the equation and multiply x by log 3 plus 1 times log 3. So this will give us x log 2 subtract log 2 to equal x log 3 plus log 3. Now here, I'll move the terms with the x to one side of the equation, move the others to the opposite side of the equation. So I'm going to move the log 2 to here, and I'm going to move this to the other side of the equation to collect like terms. So I have x log 2 subtract x log 3, which will equal log 3 plus log 2. Here now, since x is common to both these terms, I will take the common factor of x outside. This will give us x outside of log 2 subtract log 3, which equal log 3 plus log 2. So now, since x is being multiplied by log 2 subtract log 3, x will equal log 3 plus log 2 over log 2 subtract log 3. In calculating this on the calculator, I can see that x will be approximately negative 4.419. So here we have the same thing. Again, we had one power subtract another power. What we're going to do is move this power over here to have a power on each side of the equation. If you wish, you could pause the clip now and attempt the question on your own. We have to take the log of both sides of the equation. Once again, this will work for any exponential equation, whether the basis can be written the same or not, or whether the equation can be written with the same basis or not. Just taking the log of both sides will work. And so we have x, we're using the power law here, we use the distributive property. And so now we'll move the x terms to one side of the equation and move the other terms to the opposite sides. We have x log 5 subtract x log 7 to equal log 7 plus 2 times log 5. Now once again, all these logs are base 10. We can use the calculator to calculate it. We have a common factor here now of x, and so I'll take the x outside. That'll give us log 5 subtract log 7, which will equal, I could combine this to one single log, log 7 plus 2 times log 5 using the laws of exponents, or the laws of logs rather. Now we'll divide both sides by log 5 subtract log 7, so x will equal log 7 plus 2 log 5 over log 5 subtract log 7. And this will give us approximately negative 15.35. Now, let's have a look at this example. There's two methods here. One from Unit 6, or rather Chapter 6. We can change both 4 and 8 to a base of 2. This will give us 2 to the power of 2, all to the 2x, which will equal 2 to the 3, all to the x plus 1. This will give us 2 to the 4x is equal to 2 to the 3x plus 3, using the distributive property, of course. And then, since the bases are the same, we can make and they're equal to each other. We can make the powers equal to each other. This would give me 4x subtract 3x equals 3, so x would equal 3. Now also, we can do it in such a way that we take the log of both sides of the equation. That is not the only method we can use. It's the only method we would be able to use if the basis, we could only use this method if the basis can be written as bases as the same basis, rather. So if the powers can be written to the same basis, this method will work. Yet, if it's not, as we've seen in the previous few examples, we could use this method where we take the log of both sides. And so we bring the 2x in front to multiply by log 4 is equal to x plus 1 times log 8. And so we have 2x log 4, which will equal x times log 8 plus 1 times log 8. And so I'm going to move this to this side of the equation. 2x log 4 subtract x log 8 is equal to log 8. And we have, taking the x outside of 2 log 4 subtract log 8 is equal to log 8. And now we want to get x by itself. We're going to isolate x to solve. So we're going to divide both sides by 2 times log 4 subtract log 8. X will equal log 8 over 2 times log 4 subtract log 8. And this will also give us, when we use our calculator to compute this, this will also give us 3. So now there's two methods to be able to do exponential equations which can be written of the same, which powers can be written of the same basis. Now this method will always work. This one method, the first method, will only work if powers can be written of numbers with the same basis. So in summary, if two expressions are equal, then taking the common logarithm of each expression maintains equality of expressions. For example, if m equals n, then log m base 10 is equal to log n base 10. Remember, this is log m base 10. Base 10 is the one that we can use to calculate with our calculator. Where m is greater than 0, n is greater than 0, and m and n are real numbers. If an exponential equation contains one power with an unknown in the exponent, you can solve the equation algebraically by taking the common logarithm of each side. Sometimes an exponential equation can be solved by writing both sides of the equation with the same base and setting the exponents equal to each other, solving for the unknown. But this method will only work if each side of the equation can be written with the same base, whereas this method will work for all cases.